Good morning. Thank you for joining us for today's seminar for Research Contract 12-3112 titled Improving Chemical Mechanism for Ozone and Secondary Organic Aerosol. Additional information about the speaker as well as a slide and other material can be found at the link shows in this slide. For those of you online, the question for the speaker can be sent to the website as shown here. It is sierra@calipa.ca.gov. And I also need to, as part of our rule, need to quickly cover a little bit about the housekeeping item. Please look around now and identify 2 exits closest to you. In the event of a fire alarm, we are required to evacuate this room immediately. Please do not use the elevator. We will exit down the stairway and to a relocation site across the street. Now I'm going just very briefly take a minute or two to cover some general overview on this topic. Regulatory effort to attain fine particulate matter standard require improvement in our knowledge of the factor controlling concentration, size, chemical composition of PM2.5. While many advances have been made in measuring and modeling inorganic species found in the PM2.5, we still know much less about the organic fraction. Yet, organic aerosol is a major constituent of airborne particle of about 20 to 70% of the PM2.5. Organic aerosol can be emitted directly from combustion sources or formed from gases species in the atmosphere referred to as secondary organic aerosol or SOA. Graph in this slide shows PM1 or submicron particle, which is based on the aerosol mass spectrometer field Cambian at many locations in Northern Hemisphere. Primary OA is directly emitted from the fossil fuel combustion and other sources. However, most of organic aerosol at many locations is oxygenated organic aerosol, and there is a strong evidence that most atmospheric OOA is secondary. With reference to the secondary organic aerosol, as shown in this schematic diagram, SOA are formed in the atmosphere through reaction of volatile organic compound to form low volatility product which can form new particles or condense onto existing particles. SOA can account for over 50% of organic aerosol under certain conditions, and primary sources of SOA are gasoline, diesel vehicle, cooking, biomass burning, and regional biogenic emission. However, it is expected that SOA contribution will become more important in California due to the success of our program on various pollution control and mitigation strategy for traditional sources such as motor vehicle. And finally, I'm just going to take a minute, introduce today's speaker. Of course, Professor Kappa is a well-known scientist, especially to those who are working in the field of the similar that he is conducting. Dr. Kappa is a professor and vice chair of the Civil and Environmental Engineering Department of the UC Davis. He received his PhD from University of UC Berkeley in physical chemistry in 2005. Research in Professor Kappa's group focuses on understanding and characterizing the process that drive variation in chemical, physical, and optical property of atmospheric aerosol, both through the extensive field experiment and field lab experiment and field observation. He's currently leading project funded by NSF, the Department of the Energy Atmospheric System Research, US EPA, and NOAA to develop clear linkage between particle composition, including organic component and optical properties. Dr. Capo, please.
Great. Thank you, Nezat, for that nice introduction and the chance to speak to everybody today. It's nice to see some friendly faces in the audience in the back that I recognize. I have the pleasure of telling you about the work that I've done with a number of other people, in particular Professor Mike Kleeman at Davis and Tony Wexler at Davis, and then also with John Seinfeld at Caltech. And this has been a highly collaborative effort to put all this together. And I'm going to only, of course, have a chance to give you an overview of our entire project today. There is a detailed report if you want all the details, although I'm happy to, of course, answer questions as well. Our overall project is focused on trying to improve the representation of organic aerosol and secondary organic aerosol in particular, and of ozone in air quality models. And so I'm going to break this down into three parts for today, kind of the three parts of our report. The first is where I'm going to spend most of my time, which is improving the representation of secondary organic aerosol in air quality models. So we'll spend a lot of time there today. And then we'll touch on a bit the work that we've done, and in particular Melissa Venichek, who's here in the room, has done on updating modeling scenarios for reactivity assessment. And then we'll just really quickly highlight the work that we did to think about organic nitrate mechanisms and their impact on secondary aerosol in the end. So let's start with part one, improving SOA models, improving SOA. So when we proposed this work a little while ago now, kind of the state of the science that was going on in terms of how the formation of SOA was represented was through fairly simplistic models such as I have written here on the left, where I've kind of illustrated the general chemical scheme that people would use, where you start with some volatile compound, some VOC, volatile organic compound, that would get oxidized in the atmosphere. And what would happen within the model is that we'd say that that VOC reacts and it forms two things, usually two, maybe one thing, depends. And those two things would have some properties that would be assigned based on some sort of fitting to laboratory data. And that's all that these things would do. You'd have a VOC, it reacts, it forms two things, and then those two things might stay in the gas phase to some extent. They might condense into the particle phase. And that's all that they would do, right? But we know that molecules don't react like that in general. They do a lot more than just react once and stop, right? And so predictions using what I'm going to call this end product SOA model, in this case 2 products here, 1, 2. These were what were used in general, and overall what was found is with these types of models, here's 2 examples on the top here is a plot of the SOA formed. And we have measured versus modeled. The circles are the measured versus the model, and you can see the model dramatically underpredicts in this one environment. And on the bottom here is a summary of a few different studies where we have the ratio between the modeled, or the measured and the modeled as a function of how much time it's spent in the atmosphere aging. And we see that the measurements are much higher than the models in general. And so we wanted to try to improve this situation. And the way that we thought we could do this is to use a chemical model that I had built that takes into account the more complete oxidation chemistry of these VOCs and tries to then get at the properties and the reactivity of those molecules a lot more to understand their dynamic partitioning between the gas and the particle phases in the end. So we're going to try to move beyond this 2-product model. And so as part of this overall project here, this part one, I'm going to break this down into three different things. So first is the model that we've developed. We'll talk a little bit about what that is. We call it the statistical oxidation model. We'll talk about the principles behind that. We'll talk about something that we kind of stumbled onto that turns out to be really important for representing SOA in air quality models. And that's really accounting for a previously unaccounted for experimental artifact. So we'll focus on a bit. And then we'll talk about implementing all of this in the air quality model and seeing how it improves things, or how it changes things. So first, the model that we're using, as I described it, right, what we're trying to do is go beyond that simple end product formulation to take into account the actual chemistry of molecules a little bit more, right? Now you can imagine you could go to the limit of thinking about how every single molecule actually reacts and everything that it could possibly do. And some people do this, right? There are some really complex models out there, but those are the types of things that are never going to end up in an air quality model, right? They're just too complex. You got to find some sort of intermediate ground. And so the approach that we took was to try to come up with a set of rules that kind of govern the general chemical aspects of reactions, and then to apply those rules and parameterize our model based on a set of chemically oriented rules in the end. And so what we end up with is what I call a multi-generation model. So we account for not just the reactivity of the first VOC, but also the products of that, and the products of that, and the products of that, right? So we have multi-generation functionalization. So that's if you take a molecule and you oxidize and you basically make it bigger. You add oxygen to it. You add a nitrate group to it. You add something else. You functionalize it. Or you make that molecule fall apart, because sometimes reactions make molecules fall apart. So we have functionalization and fragmentation accounted for in the model. And then we also have to think about the likelihood that that molecule wants to exist in the gas phase versus the condensed phase, right? It's going to partition, and that depends on its volatility, in the end, its vapor pressure. And so in our model, the way that we represent this is we came up with some rules that basically describe molecules. It's a simplified representation of molecules, right? Because we have to simplify somehow, where we just say that molecules are basically combinations of carbon atoms and oxygen atoms, right? That governs most of the properties that we care about in this case. It averages over some other things, right? We can't get all that detail and still make it tractable. So we found that this is a reasonable simplification to make. And then within this space, if we think of a molecule here, so for example, a C10 molecule, right? If it gets oxidized, we might add some functional groups, so functionalization adds oxygen atoms, right? Or it might fall apart instead of just functionalizing, and it might move into this space as they react, right? So we can think about what rules might govern this behavior, and what we have to come up with is rules that govern the reaction rates of those molecules and how those vary within this space. And we can use chemical tools to do that, thinking about structure-reactivity relationships or observations to constrain those. So we've done that. We can think about the product distributions that we might get overall here from functionalization or fragmentation, and that's going to be governed by physical and chemical constraints on how molecules tend to react. We can think about what the volatility or vapor pressure of these molecules or species are, right, which is going to be governed by basically how big they are, how many carbons they have, how many oxygens they have in the end. And then we can think about the probability that when a molecule, or a species, I should say, these aren't really molecules anymore, right? They're species, reacts, that it's going to functionalize or fragment, and what that probability is and how that varies throughout this space, right? So in the end, we end up with only 5 tunable parameters within this model that can describe all of that chemistry in the end. And so one is really a probability, a tunable probability of functionalization versus fragmentation. And this probability ends up being a function of how many carbon atoms you have and how many oxygen atoms you have. We have how much does the volatility change when you add an oxygen or when you fragment, right? When you move through this space. That's going to depend on what actual functional groups you're making, right? So that's kind of where we get some averaging between if you have an alcohol group or a ketone or a carboxylic acid. All these different things get averaged together in some average behavior in the end. And then we have some probability that when you functionalize, do you go from where this red dot is, just up 1, you add 1 oxygen? Do you add 2? Do you add 3? Do you add 4? How many do you add in the end based on the chemistry that might happen for that molecule in the end, right? So these are all tunable and parameterizable in the end, and all the details of the model are available in these papers and the report. So here's just one example of how that works for one species. This might be a bit much, but in case it's helpful, right? Here's a C10O2 molecule, right? Or species, I should say. And what happens? It might react with an OH here with some rate coefficient. And based on what this species is, it has some functionalization probability. And it can form 4 functionalization products here in the end, right? It can add 1, 2, 3, or 4 oxygen atoms with some probability for each one of those, right? And the sum of those probabilities has to be 1. So we have those 4. And then we have all the fragmentation products that you can get, which is basically the probability of that's just 1 minus the functionalization probability. And then you have all the potential fragments that you might have. And so one could ask, well, how do you define what those fragments are in the end? And that's hard to know because molecules can kind of fragment anywhere, and they do so a little bit randomly. There's some governing behavior behind that. But the simplest way to deal with that is to just assume that they all have an equal probability, because that's actually probably not that far from reality in the end. So we make that simplifying assumption that the probability of getting an individual fragment is the same for all of these different fragments in the end. So the fragmentation probability there is just 1 over the number of fragments that you have, right? So that's a simplification that we have to make. We can make other assumptions, and you just get different parameters out of your model. It still actually works if you make different assumptions. We found it's not especially sensitive to that, but you do have to include this fragmentation. Yeah. Any questions right now? Of course.
Have you noticed any, have you accounted for occurrences when that red dot could potentially move leftwards? I mean in case of polymerization or oligomerization happening in the gas phase.
So in the gas phase, there is some evidence now, since we've done this work, that you can get accretion reactions making dimers within the gas phase. We are not accounting for that here. It hypothetically could occur, right? And we see that occurs for certain types of systems. We haven't accounted for that yet in the gas phase. We've done a little work with that in the condensed phase, but we haven't included that here in detail yet. Yeah. And so I can repeat the question. The question was, can you basically move to the left in this grid here from a C10 and suddenly have 2 of those stick together and make a C20 molecule?
If I may, I would appreciate if we could hold the QA part at the end of Dr. Capo presentation, because when you have your question, I need to bring the microphone to your attention so people online can hear it as well too. So thank you so much.
All right. And in the gas phase, that's probably not that important. In the particle phase, oligomerization certainly is important. All right. So we have this basic chemical framework now, right? This simplified chemical framework. We still have to come up with the right parameters for that model, right? Because it's not an a priori model, right? We have to parameterize it somehow. And so we used observations from the Caltech Environmental Chamber. They have a very nice set of measurements of SOA formation. And so here we have in 2 graphs the SOA concentration in the chamber as a function of reaction time for 2 different systems here, toluene plus OH and alpha pinene plus OH, for example. And what we have is in the circles are the observations, and then the red lines are our fits to those observations, tuning each of those adjustable parameters in the end. So you can see that we can fit the data quite well in the end to determine our optimal parameters. And we've done this for a variety of different anthropogenic and biogenic VOCs, the common ones that we find in air quality models. Monoterpene classes represented by alpha-pinene, isoprene, the largest biogenic species emitted worldwide. And then we have our key anthropogenic species, benzene, toluene, xylene, our aromatics there, plus our alkane representative here with dodecane and the isomers of dodecane, right? So we do this, we have chamber experiments that were performed under both low and high NOx conditions, right? The NOx amount can affect the chemical pathways that a molecule is going to take, and so you end up with different parameters, whether you're under low or high NOx conditions in the end. And we fit to these time-dependent profiles, which will become important here in a minute, because thinking about this time dependence is actually different than how people have traditionally fit chamber experiments, where they just look at the amount of SOA formed versus the amount of precursor reacted without accounting for time. It turns out that time is really important here because of dynamics that go on in the chambers, which we'll talk about here in a minute. So I think this time-dependent framework is an important way to look at the formation in chambers. And then one other thing that I'll note, and we'll bring this up later a little bit, is that because we keep track of at least this approximate atomic makeup of our species in our model, right? We have carbon and oxygen. We can have a prediction of things like the oxygen to carbon ratio, which modern instruments can now measure in the field, and we have a large database now of these oxygen to carbon ratios as well. So this gives us another constraint on our measurements in the end, and our modeling and how well it's doing. And the traditional models don't have that information at all. Okay. So that's part 1A. Part 1B now is the thing that we kind of stumbled into. I mean, we knew we should look, but it turned out to be really interesting and really important. And that is the fact that all of these chamber experiments, right? So we use chamber data to parameterize our model, against which we parameterize our model. And so you can't really see this picture very well here, but that's a picture of a Teflon chamber, right? And so yeah, these environmental chambers tend to be made of Teflon in general. And it turns out it's been known for a couple decades that things like ozone, reactive species, can be lost to the walls of chambers, and you need to think about that a little bit. But what people hadn't really thought about until just a little bit before we started this work was that some of the lower volatility species that might be formed as part of SOA production can actually not just stick to the walls, but absorptively partition into Teflon. If you think about Teflon, right, it's actually a little bit fluid. That's why it's kind of soft, right? It's not exactly a wax, but stuff can dissolve in Teflon. We think of it as inert, but it's not quite as inert as we like to think all the time. And so Paul Zeman's group really pointed this out with some beautiful experiments using single compounds at a time to kind of probe this effect. And then we built on that to think about, well, how does this actually impact on SOA formation? Okay? And so what we did is a couple things. One, we built this process, this loss of vapors to the walls of the chamber into our model, so we could have that as part of the model. But then another important aspect was, well, how do we quantify that? How do we figure out the appropriate rates? And the way that we did this is we actually performed, or I should say John Seinfeld's group performed experiments where they did the same chamber experiment over and over, where they put in the same starting amount of VOC, the same kind of OH precursor concentrations. Everything was the same except for they changed the amount of seed area that they had. So they injected seed particles, so ammonium sulfate particles, into the chamber onto which the SOA could condense. And by increasing or varying the seed concentration, what you do is you change the competition for where those molecules want to go. You can imagine a molecule might go to the particle or it might go to the walls, right? And what happens is if it goes to the particle, if it's high volatility, if it's a high volatility species, it'll go to the particle and it might come right back off. And it can go to the wall and come right back off. If it's intermediate volatility, a vapor molecule might go to the particle, it might hang out there for a while, and then eventually come back off. And if it goes to the walls, it might go there and eventually come back off, right? So you introduce a time dynamic to that process where stuff gets kind of trapped in one phase or the other until it ultimately reaches equilibrium. Or if they're really low volatility, basically if the vapors make their way to the particle, they just stay there, right? Or if they make their way to the walls, they just stay there. So to think about these vapor wall losses, you have to think about them in context of what the volatility of the species are, and then what the rates are associated with a vapor molecule making it to a particle versus making it to the wall. So you can think about this vapor wall rate coefficient is essentially constant for a given chamber, but the vapor particle rate constant is going to depend on how much seed surface area you have in the end, right? How likely that molecule is to run into a particle versus the wall, right? So you can change those relationships. And so by varying the seed, we can actually tease out what these loss rates are, what these relative loss rates are, and try to then correct for this vapor deposition onto the walls. And so what we did is we fit our observations both with and without accounting for this vapor wall loss. Okay. And so we did this for a toluene plus OH system in particular, and then applied our findings to all the other systems that we've studied as well. And this is just an example of the types of results that we see. So going from the bottom to the top on these two graphs, we have the bottom is when we have very little seed initially, and you can see if we look at, on a long time scale here, you make about 40 or 50 micrograms per cubic meter of SOA. But if we look at when we have a lot of seed aerosol, we make 80 micrograms per cubic meter in the chamber, right? So here, by basically increasing the competitiveness of the particles relative to the walls, we doubled the amount of SOA that you formed. We didn't change the chemistry, we just changed where the molecules go, right? And so we can account for this, and we find that, in the end, if we just think about the fact that the atmosphere, right, I mean, yes, there's the ground and everything, but in general, in the atmosphere, there's no surfaces except for the particles, most of the places that particles are. So SOA formation in chambers is going to be suppressed to some extent relative to the actual atmosphere. The extent of that suppression is going to depend on exactly how you operate your chamber, right? Exactly what the conditions are, exactly what the molecules are, and the chemical processes that they go through. So it's going to be variable. But in general, we'll find that things are suppressed. So we developed a new parameterizations that do account for this wall loss. And we're going to look at the impacts of that. We found that for the experiments here, right, we see this factor of 2 pretty clearly. And so we wanted to understand then how does that play out in an air quality model, right? Yeah. So let's move to the actual modeling, right, the 3D modeling now. So what we ended up doing is we merged our statistical oxidation model here with the SAPRAC gas phase mechanism. So SAPRAC's routinely used to predict all the gas phase stuff that's going on. And we used SAPRAC then to drive the oxidant concentrations that would oxidize the VOCs and the SOM species that form SOA. So that's kind of where that interaction is. SAPRAC drives the oxidation of the species that form SOA. But just one little note here, kind of a technical note, is that because we have all these new species now that we've introduced that are not part of the normal SAPRAC framework, right, all of our SOM species, we don't want those to deplete the oxidant pool because SAPRAC wasn't built with those molecules in it in the first place. So we just recycle OH to pretend that they had no effect. Right? Just a technical note there. So Mike Kleeman's group and Shantanu Jathar, as part of that, made a mechanism generator that would turn everything that I did into Fortran. I don't know Fortran, I write in other languages, so he made it work in a language that works for 3D air quality modeling. And we integrated the SOM model into the UCD CIT air quality model framework. We chose to use the UCD CIT in particular because it is well suited to dealing with large numbers of species right away. CMAQ can do that, but it's a lot harder. It's not as well suited for increasing the number of species. And even though we're using a simplified representation of the chemistry, we still have a lot more species than just the two product models that you started with. So we worked with the UCD CIT here. We ran simulations using both our low NOx and our high NOx parameterizations. Okay, and the low NOx here is referred generally to as the high yield simulations because the amount of SOA that you make from a precursor reacting tends to be higher when you have lower NOx around and vice versa. And then we're going to compare our SOM output with what I'm going to call the base SOA model, which is kind of that standard two-product type model that we've seen before. And then with what I'll call a cascading oxidation model, which I'll describe here in a minute. And then we're going to do this separately, both with and without our vapor wall loss effects. So we can understand all these different effects separately. So the base model here is basically as implemented in CMAQ 4.7, the SOA formation there. So this is essentially the two-product formulation in the end. And just to note, it lacks this multi-generational aging in the end. Those are the key factors there. Our cascading oxidation model, I call it kind of a reactive two-product model as we've implemented it for testing purposes here, where we start with, you could say, here's our two-product model on the top, but then these two products can go on to react, where the higher volatility product reacts to form a lower volatility product, and then the lower volatility product reacts to form a non-volatile product with no fragmentation accounted for anywhere. You might wonder, why would we do this? Well, because people are doing this. Right? People have done this as a way to ad hoc account for the effects of multi-generational aging without going back to the original chamber experiments to say, maybe we shouldn't account for multi-generational aging after already fitting our data. Right? We should account for it while we fit our data. They didn't do that. So we wanted to understand how this might compare. Also, these aging reactions that are implemented when people do this are generally relatively unconstrained. And as you might imagine, you basically enhance the SOA yields when you do this because you take stuff that was semi-volatile and you just force it to be non-volatile on some time frame. Okay. All right, so let's start with our SOM model versus the base model. And I'm going to start here with stuff that doesn't account for the vapor wall losses. Okay. Just so we can get a sense of what the addition of constrained multi-generational aging alone does, right? And so on the left, so on all of these, we're going to have on the top is the South Coast Air Basin, and on the bottom is the Southeast US here. We did simulations for both. And what we see is, so we have our base model over here on the left, the SOM model in the middle. They're on the same scales, and they don't really look very different in the end. And if we take a ratio between the two, we actually see that indeed they're not all that different. You do get larger differences as you move away from, you could think of it as from the source regions, right? You get somewhat larger differences. And so when you move away from those source regions, the differences go up a bit, representing, we think, that's the influence of accounting for multi-generational aging. It tends to have impacts on, think of it as longer time scales further from sources in the end, but the differences aren't in the end that big when we add the multi-generational aging. We can look at that here another way. So on the left are some bar charts here showing, so we can compare, I know this is a little hard to see, but let's say our low yield base simulation here versus our low yield SOM simulation in 4 different regions, 4 different cities, and we see that you pretty much get the same number, right? And if we look at the high yield as well, you get more, but you get about the same concentrations again, in these particular locations. You do get a little bit of a shift in what we think forms the SOA, right? You do get a little bit of a shift in which precursors contribute at what percentages, right? But in general, things actually look similar here, right? And in the end, this is reflecting the fact that while we accounted for the oxidation chemistry, certainly in more detail and more realistically, in the end, those original models were still parametrized against similar chamber data. And this suggests that on the time scales, at least that matter to some extent, those parameterizations, right, those really simple two-product parameterizations, they basically wrap in the multi-generational aging. They just kind of stick it all into those two parameters in a way that ends up at about the same answer in the end, in terms of the total mass. So we do think we're doing a better job. You know, we're representing it more realistically, but it doesn't have, in this case, a big impact on the concentrations, right? This doesn't alone, for example, close that gap that we saw between the model and observations. Now, one core thing that does change that is of potential importance here, which is that if we look at the distribution of the species, so if I take all the species in the SOM model and I look at the species in the base model, the two-product model, and I look at their volatilities, right? What their vapor pressures are, and I look at a distribution of those volatilities, what we find is that the SOM predicts much lower volatility SOA overall than the base model. And that's actually a natural consequence of the inclusion of the multi-generational aging. But where this is important is that the base SOA model will now be more sensitive in general to dilution, because this stuff would evaporate if you dilute, and to temperature changes, because this stuff would evaporate when you increase temperature. Whereas this stuff will mostly just stay in the particle phase, because it's low enough volatility. All right. What about versus the COM type model? So if we look at the COM type models, so left is SOM, right is COM, top is SOCAP, bottom is Southeast US. You can clearly see the COM type models make a lot more SOA, right? When we basically force everything into the particle phase, you make more SOA. Not too surprising, and these are very large differences in the end. As I alluded to earlier, this is really because in the COM models, you're just double counting the carbon. You already parameterized your model to give you about the right answer, and then you just forced all the remaining gas phase carbon into the particle phase, right, in an unconstrained way. People had done this a little bit. This was argued to do this for certain types of species, but not others, because, hey, it made our model look better compared to the observations. As far as I can tell, that's the argument for including these types of models. We think that this is just double counting, and really, you might be getting a better answer, but it's undoubtedly for the wrong reason in the end. And so we suggest people shouldn't do this. All right. So what is a potential solution? Is actually these vapor wall losses that I talked about. So now if we start to include the vapor wall losses, so on the left here is the base our SOM simulation with no vapor wall losses. Okay? And then we're going to take the ratio between when we include vapor wall losses and this no vapor wall loss system over here. Now it turns out we actually are doing this in two limits. We have what we call the low and the high loss cases. We have these two limits because at the time, based on the chamber observations and our modeling efforts, we could only constrain the vapor wall losses so well. We got them pretty good, but you know, there's some range, and so we wanted to just kind of capture that range to understand the potential impact here overall. So if we look at what we call our low case here and our high case, they have similar spatial distributions in terms of these ratios, but we see much higher ratios, of course, in the high vapor wall loss case than the low. And we see also that this ratio is lowest kind of in what we might consider the source regions, and higher as we go away from sources in the end. The impact of including these vapor wall losses seems to it has a substantial impact kind of everywhere, but certainly more so as we move away from the source regions. And we can see this also in the SOCAB as well as the Southeast US, where the Southeast US down here has a lot of biogenic emissions naturally from all the trees down there as well. Thinking of this idea that we have more outside of major source regions, we also see that if we take the ratio, again, this is that ratio between the simulations with vapor wall losses versus without vapor wall losses, right? If we take that ratio and we plot it versus just the absolute amount of SOA, and we do this for SOCAB versus the Eastern US, we see that indeed that ratio goes down, right? The bias in the model goes down as you go to higher and higher concentrations overall. But even as we move towards higher concentrations, we see things plateauing in one case towards about a factor of 2, and in the other case maybe about a factor of 4 or 5 here as well. So pretty substantial impacts even in those limits in the end, right? And this factor of 5 here in the Eastern US is not that dissimilar from what happened when you take these COM type models, right? But now we're putting a physical reason for explaining this. Things that happen when you do this is you increase the amount of SOA. You don't affect your primary organic aerosol, so your SOA to POA ratio changes, and that's illustrated here. The fraction of total OA that is SOA, and you move from basically a POA-dominated system here in SOCAB on the top left to an SOA-dominated system here on the right. And it turns out this SOA-dominated system is most consistent with the observations that we have in these regions in the end. So we think that things have improved in that direction. We can also look at our dilution normalized or dilution corrected diurnal profiles that were observed. In this case, these are measurements from the SOAR 2005 study in Riverside. And what we have is the OA normalized by CO here ratio as a function of time of day. And on the left is with no vapor wall losses, then low and then high. Observations are in the orange with the gray bands kind of indicating our estimated range of variability. Or sorry, yeah, that's right. And then the model results are in these box and whisker plots over here on the top. And what we see is when we don't have vapor wall losses, yeah, you get a little bit of a bump during the day, but you don't get much because SOA is not contributing that much. You're POA dominated. And then as we move to this high case, we actually start to match the observations a lot better. We're not all the way there, but we're definitely closing that gap and providing a physical explanation for it. Not only do we do better in terms of the absolute OA abundance, we actually do better in terms of this predicted O to C ratio that we have as well. Right down here, we don't see much change at all on the bottom left compared to the observations. And then when we include vapor wall losses, we start to do a lot better. We get a lot stronger diurnal variability, and in fact, the absolute values do a lot better. And this is an indication, again, that you're really becoming SOA dominated here, especially during the daytime. Right. So to summarize kind of results of this part 1 here, we think that when we include multi-generational oxidation in a realistic way, it does improve the simulation of the SOA properties, but it ultimately has little impact on the absolute SOA concentrations relative to the base model, right? So we think that we're doing a better job representing the chemistry and the spatial distributions, but it doesn't actually impact the absolute amounts that much. If you do use these unconstrained COM type models, you can increase SOA a lot, but you're probably getting a better answer for an unrealistic reason. And so we definitely encourage people not to do that anymore. We found that losses of semi and low volatility vapors to the walls of chambers do bias SOA formation low in chamber experiments. It depends, again, on how you operate your chamber, what the magnitude of that bias is going to be. But when you account for that, and when we implement this in a 3D model, we find that the influence of the accounting for these vapor wall losses can really lead to substantial increases in the amount of SOA that you form, and we think actually improvements relative to measurements as well. So we think that we're doing a lot better here. And this vapor wall loss is one of the driving things that really helped. All right. Where next with all of this, just to think about kind of what we think still could be done. Just, this is not an exhaustive list, but one thing that we didn't fully account for here is the semi-volatile POA components, and so we need to start to account for that, which we think will help improve spatial distributions even further. Thinking about under-recognized sources or precursors of SOA, such as low volatility consumer products, which have recently popped up as being of potential importance to SOA. Thinking about how SOA is likely to respond to future changes in the photochemical environment, in particular the NOx changes and the NOx VOC changes that are going to occur. And then not talked about here, but we focused on summertime here with all of our simulations, but in places like the San Joaquin Valley, there is actually a fair amount of wintertime SOA. And it's proving challenging to explain all of that so far. So a greater focus on the wintertime could be useful as well. All right, so that's the majority of the talk. The rest will go faster. But part two is thinking about ozone instead of SOA, and improving modeling and updating modeling scenarios for reactivity assessment here in the end. So for those who are unfamiliar, we are interested in the incremental reactivity of VOCs in the atmosphere, and in particular, the maximum incremental reactivity. So that's the amount of ozone that you, additional ozone that you produce for a change in the from some addition of a given VOC, right? So kilograms of ozone produced per kilogram of VOC that you introduce in the end. Understanding these MIR values does provide guidance on control strategies, right? Which VOCs you might want to target if you're focused on ozone. And the representative urban atmosphere in which these maximum incremental reactivity values are determined hadn't been updated since 1988. Yet we've had substantial changes in urban air composition over the last 30 years, right? So one question is, to what extent have these MIR values changed over the past 30 years due to all the changes in kind of the atmosphere itself in the end? So I should say this is all work done by somebody here in the audience, Melissa. And what she did, really, I had nothing to do with this work. I just get to talk about it. Is looked at how the MIR values are impacted by updating the representative urban atmosphere to 2010 conditions in this case, accounting for meteorology changes, emission rate changes, concentration changes, and composition profiles of what we have in the end. So here they explored box model scenarios for 39 different cities, looking at averages and medians across all of these. Looked at a whole bunch of individual compounds and compound mixtures here, 1,233, and developed city-specific modernized VOC compositions or surrogate profiles in which to allow everything to react, kind of the background composition here in the end. How were cities picked? Well, we started with the 1988 list of cities and then threw a couple out and brought a couple in based on changes over time. And so added Fresno and Bakersfield, so a little more California, and got rid of Chicago and Tampa, which haven't shown as many exceedances with respect to ozone in more recent years in the end. Otherwise, it was largely the same as the 1988 list in the end. Updating the meteorological conditions, the WRF-Chem model was used to determine the conditions during ozone event periods for each city. And what was found is that overall, so the box and whiskers here show the 2010 values, and the solid lines were the 1988 median values, and we see that there's a general slight decrease in temperature, and this is all as a function of time of day here. So a slight decrease in temperature overall. a pretty clear decrease on average in the planetary boundary layer height, and then a decrease overall in the absolute humidity overall. And these changes in the end were primarily driven by shifts in the seasonality of when you got the peak ozone. Not for every city, but for enough of the cities that it moved things around a lot. Okay. Emissions have gone down from cars a lot, cars and trucks, and so we see a lot of decreases in the anthropogenic emissions of non-methane organic compounds shown in the top 3 plots, especially around the rush hour period. If we look at the biogenics, they don't change that much. They're on the bottom here, bottom right. There are still some improvements in how they're represented. We've learned a lot in the past 30 years on how to represent biogenic emissions, but in the end, not major changes overall relative to 1988. The overall composition of kind of our representative atmosphere has changed over time in response to these changes in emissions. And so you end up with, in the end, the summary point is that you end up with a larger fraction of these oxygenated species, the alcohols and ketones in related species overall, and an associated smaller fraction of alkanes and alkenes and aromatics, right? The basic anthropogenic versus biogenics reflecting that shift overall. So we have a different reactive atmosphere. All right. So with all of those changes, what do we see? We see that for one, the 2010 median MIR value, so across every city, relative to the 1988 values, we see that there was a decrease of about 20% on average, right? The slope of this line is 0.8. So the MIR values all decreased on average. The magnitude of this decrease tended to be largest for the things that had the smallest MIR values. We might see that if this was a log-log plot here, but you can see that on this bottom left plot here with this kind of upturn at low values. But overall, we see that it's relatively independent of where you are. Why do those changes come about? Right. We can break this down. So Melissa ran simulations where they isolated the meteorology, the emissions, and the VOC profile separately. And it turns out that the meteorology changes dominate things in the end. And I think a lot of that is the boundary layer height changes, and with some effects of the temperature in the water. The emissions do have an impact as well here, just not quite as large in the end, but the emissions changes do have an impact. And that's going to be really the NOx to VOC ratio that's changing there over time. And then the VOC profile itself does have some impact as well, right? The atmosphere in which you're doing this has some impact, but a smaller impact relative to these other parameters. If we think about, the compounds that we're looking at, though, the ones that in 1988 had the highest MIR, they continue to have the highest MIR. By changing the composition of the atmosphere, by changing the reactivity of the atmosphere, we haven't shifted things around in terms of how individual compounds react very much. There's a few compounds you can see that stand out here, right, that did have major shifts because of the changes in the atmosphere. But by and large, the ranking is similar, so we can still think, well, we should probably still target the same compounds if we want to reduce ozone, right? All right. So just to summarize here, updated the emissions, meteorology, and concentrations of reaction scenarios here for assessing incremental reactivity. The MIR values all decreased by 20%, largely driven by meteorology, but also driven by decreases in emissions and the changing NOx to VOC. But we find that the compounds that had the highest MIR values in 1988 continue to today. All right. So last part, very quickly here, is thinking about how organic nitrate and N2O5 chemical mechanisms impact secondary aerosol formation. And I'm going to focus here on organic nitrates in particular. So when a molecule reacts in the atmosphere, if it reacts with an NO3 radical, or if it reacts in the presence of NOx, some of the species that you can form are nitrogen containing, right? The nitrogen sticks into the molecule and you make a nitrate group. Those molecules, those nitrate molecules have particular properties. They can go into the particles, and when they're in the particle, when they condense into particles, they can hydrolyze in a particle. The organic part is probably going to stay in the particle, but the nitrate part might get popped out again depending on basically the amount of ammonia that you have around to determine its partitioning. So these organic nitrates weren't represented very explicitly in the past. Havilah came up with a nice way to do all of this, and so Mike Kleeman's group implemented all of these reactions involving a suite of different organic nitrates, in particular biogenic species, which we think are more likely to form them. And this includes gas phase production, gas particle partitioning, and hydrolysis, and had to add a lot of reactions here to cover everything. And then they evaluated the impact of adding all of these reactions on SOA predictions for 2 periods, or seasons, or locations, depending on how you want to look at it. The SOCAB in summer, in 2010, and the San Joaquin Valley in winter in 2013 here. What we find is there's a larger influence of this expanded mechanism predicted for summer rather than winter. Largely, that is reflective of there's just more SOA in the summer than winter, so you can have a bigger delta more easily in some ways. But some of that is related to the actual chemistry that's going on as well. The things that dominate for these nitrates are the monoterpene nitrates. So you form a lot of those, and then glyoxyl and methylglyoxyl nitrate species in the end. So monoterpenes are going to come from monoterpenes. Glyoxyl, methylglyoxyl will largely be derived from isoprene and other oxidation products. So in the summer, the amount of SOA that you get from these monoterpene nitrates and other nitrates is nearly a microgram in the end, so actually pretty big. In the winter, they are relatively small, only about 0.1 micrograms. Now, this has some potential influence of thinking about how NOx might influence the SOA formation. And that is one, that these monoterpene nitrates, because of the particular formation mechanisms, are expected to decrease directly proportional to the NOx. So if NOx goes down, you'll make less of these. Okay? Now, glyoxyl and methylglyoxyl SOA, though, because of the chemical mechanism involved, when you decrease NOx, they go down more slowly than the NOx, right? So you get less of an impact overall. So with a combination of these two in the end, for summertime, it was predicted here that a 25% decrease in NOx could lead to a 0.13 microgram, or we'd say about 13% decrease in the PM2.5 SOA here in the end, right? So NOx itself can actually impact the SOA through the organic nitrate pathway, not to mention the photochemical environment that drives everything as well. All right. And so with that, I'll thank everybody who contributed here. First, again, Mike Kleeman, Tony Wexler, and John Seinfeld, the co-PIs on this project. Professor Shantanu Jadhar, who was a postdoc with us at the time and did all of the SOM modeling work with me. And Mike, Melissa for doing all the MIR work. The Caltech team for the experimental work. Bill Carter's helped as well. Jose Jimenez has been helpful with providing data, and NASOP for program management. Thank you. I think NASOP will want to hand you the microphone here. Yeah.
Sorry if my question sounds stupid. I had a question about your assumption regarding the recycling of oxidants in your SOA model. Mm-hmm. So I think in the real world, both SOA precursors as well as their product species might turn out to be potential sinks for oxidants. So how do you reconcile the two conflicting ideas?
I absolutely agree. Like the species that I have here, right? If they're reacting with an OH, they're reacting with an OH. The argument is that SAPRAC has been tuned already, right, to basically get the ozone chemistry as right as it can.
Correct.
So you could think of it as the chemistry of my SOM species is accounted for in SAPRAC in the form of some other SAPRAC species in terms of how it affects the oxidant environment. The ultimate ideal would be to somehow integrate all of those, right, so that they're connected. But that's a mighty big task to do. Yeah, you have to break SAPRAC first to then fix it.
Hi, I had a question in your tables where you're showing the results of the dilution. Sorry, I'm missing some of the terms, but your experiment through the tubes where you injected an inert to capture the SO2 on the back end, the basis for your arguments. Keep going back.
Right, the
Keep going back.
SO2? We don't have anything with SO2.
Sorry, SOA. There you go. Sorry.
Sure.
So here, I noticed that the variability in the data on the back end starts to obviously propagate. Can you explain that
Absolutely.
difference?
So this is a function of the measurement. So the way that these particular measurements were done is that you inject your seed particles, and then you condense the SOA on top of that seed particle. So and then you take and you measure the volume of that, and you take a difference to determine the amount of SOA that you form. So when you have very little seed, your SOA that condenses is a lot of the volume, and up here it's less. So it's just a difference between two big numbers versus a big and a small number, and so you get more noise, or more apparent noise, I guess. Yeah.
All right, thanks.
I think you very interesting presentation. I got a quick question about the reaction time. I think in the previous slide when you showed you feed your data to the Caltech laboratory results, and the reaction time is like around 12 to 15 hours, and the other one you just showed is around like 20 hours. If the reaction time is part of your fitting, it's one of the parameters. Do you think it's representative in the real ambient atmosphere? It's a 12, 15 hours. It's a real sort of reaction time to form SOA, or does it matter?
Well, certainly the reaction, the formation time of SOA is dynamic. But if we look in LA, right, and we look at the diurnal profiles, you make SOA in the afternoon on top of a background in a couple hours, right? So SOA forms in a couple hours, but it also forms in many hours because it's a continuous process that is driven by the cycling of your oxidants as well. In terms of the chamber experiments, so these are the low NOx experiments. The high NOx experiments are actually done a lot faster, and that is a function of just how the experiment is done and how the oxidant is produced for these types of experiments. In terms of that time frame, I would argue that there's a couple things that matter. Is if you're capturing the processes well, right, and you have those within your model, it doesn't matter necessarily whether you do a long or short experiment. You can do it short, you can do it long, as long as you know the processes and can simulate those. It doesn't matter. If you ignore the processes, right? If you're oversimplifying everything that you're doing, then the short or long will matter. What probably matters more in a chamber experiment, once you account for things like vapor wall loss and the dynamic partitioning properly, what probably matters more is getting the oxidant conditions right and the concentrations of your species in the chamber, right? Because we know that the chemical pathways that things go down depend on relative concentration. So whether you end up HO2 dominated, NOx dominated, whether RO2 plus RO2 is competitive, which you generally don't want, because it's probably not so much in the atmosphere. So getting those chemical conditions right, I think, is actually more important than time.
Thank you so much.
Oh, hi, Chris. Nice to meet you. I just wonder, you compare the wall loss case with the observations based on the UC Riverside. Is that the regional model output, or do you have kind of like a regional model evaluation about your wall loss treatment in your model too?
Sure. So these plots here, in the modeling results, these box and whisker plots, are one grid cell, I think, out of this model result here.
So it's extracted from the regional model to do the comparison?
Yeah, it's not a separate box model. It's out of this.
Yeah,
it's just taken the appropriate grid cell.
And in terms of uncertainty estimates, what kind of mathematics you use to constrain your uncertainties?
So these are not uncertainties. These are just ranges of the model output. And then for the observations, this range is based on the scatter in the data as one standard deviation, as well as then accounting for lack of knowledge about the background CO concentration. So that's where we get these 3 different lines, orange lines. In terms of error propagation, that's a lot harder to do. And I mean, I think one would have to run some sort of perturbed physics version of your model where we'd come up with uncertainty estimates for each parameter. And that would be pretty challenging. And so I tend to think of things, rather than thinking about the uncertainty for kind of one model formulation, is how do we step through things if we go from our high to our low to our no, to kind of understand sensitivities to processes. That's usually the approach that I tend to take, because defining and propagating uncertainties through 3D models is certainly challenging.
Thank you.
Hi, Chris. Thanks for a good talk. I had a kind of a big picture question. I just wonder if what you've learned about wall loss is what you'd recommend for environmental chamber studies going forward. I mean, should we be looking at changing materials, not using Teflon, or bigger chambers, or different kinds of chambers, flow tubes versus smog chambers, for example?
So there's no perfect answer. Using other types of chambers isn't necessarily helpful. So for example, people have done experiments with stainless steel chambers or glass walled chambers. Stuff sticks to those too. It's just not absorptive partitioning anymore. Now it's adsorptive, but actually stainless is really bad. I don't know. You have to account for you have to account for losses of sticky things kind of wherever you are. In flow-through experiments, like flow tube experiments, there are questions about accessing the right timescales and whether you have your chemistry right, and then also whether you're getting your condensation steps right. So you tend to nucleate a lot in those, and whether that's what you want. What we recommended in general is trying to run at somewhat elevated seed aerosol to at least enhance that competitiveness, tending to run at as not quite as fast as you can, but not the really long experiments unless you can account for the processes. And then what was the other aspects? In terms of operating chambers, things that you can try to do, it's a little more challenging, so a lot of the stuff getting to the walls, so it's governed by molecular diffusion on a very narrow scale right near the walls, but otherwise it's governed by turbulent diffusion within the chamber. So to the extent that you can minimize or reduce temperature gradients in a chamber or reduce turbulent mixing, you can slow the wall loss ideally. Bigger chambers do help larger or smaller surface area to volume ratios. So that has some impact as well. We came up with rate coefficients on the order of 2 times 10 to the minus 4 per second. Some of the folks at University of Colorado now who are doing it are seeing their chambers like 10 to the minus 3 per second, so even faster. So it's kind of like there's been some work that's been done in some even bigger chambers that are seeing much less of an impact. So bigger is better, more seed is better. Beyond that, I would just argue like accounting for the processes and making sure that you understand and characterize your chamber. Because I think if you characterize your chamber well, you can account for these in your interpretation.
Do we have any question online? No? Okay. Is there any more question from audience here? So if not, let's thanks again our great speaker for his outstanding presentation. And I personally appreciate those attended in person and online as well too. The final report along with this presentation and numerous publications, they're all available online on the web link that I show in my first or second slide. So thanks again for coming.